Hello everyone, my name is Kevlin Kadamala and I'm a second year PhD student at the University of Galway. Today I'll be presenting my work Enhancing HVAC Control Efficiency, a hybrid approach using imitation and reinforcement learning. My co-supervisors are Dr. Des Chambers and Dr. Enda Barrett. So, what is the problem? Well, heating, ventilation and air conditioning or HVAC systems play a significant role in ensuring occupant comfort. But these systems account for around 40% of total energy use in buildings. So you can see if they are implemented incorrectly, it could lead to large amounts of energy consumption, in turn driving up costs while also possibly reducing occupant satisfaction. Current solutions involve rule-based controllers, but they are slowly being replaced by smart thermostats. New methodologies and algorithms like model predictive control and reinforcement learning can adapt their control policies based on different objectives or cost functions. But these algorithms and methods also come with their own drawbacks. For example, MPC systems find it challenging to deal with non-linearity in building dynamics because of complex nature building systems. On the other hand, reinforcement learning is sample inefficient. Thus, it requires significant amount of time and training resources to reach a desirable level of performance. In our work, we focus on this reinforcement learning problem. We ask the question, can we leverage already existing data to help with the RL training process? Thus, as a solution, we explore how imitation learning can help improve the performance of reinforcement learning in the application of building control systems. First, a little bit of background. Imitation learning involves training an agent to mimic a human or expert behavior. In our work, we use a type of imitation learning known as behavioral cloning to learn a policy pi from a dataset of state action pairs. Behavioral cloning has been used in HVAC control before. Since we're dealing with continuous actions, we implement the negative log likelihood function given here. Here, pi theta is the predicted probability at time step t of taking action A given state S, while H is the entropy term. Lambda is given to the entropy term for regularization. But simply using behavioral cloning is not enough. The performance of the policy heavily depends on the quality of samples provided by the expert dataset. The expert policy pi star determines the distribution of sample states X. So, the learned policy will perform poorly on unseen states. Thus, behavioral cloning often learns a policy that generalizes poorly. As a solution to this, we then fine-tune the agent that was trained using behavioral cloning using reinforcement learning. Reinforcement learning involves an agent that learns to make decisions by taking actions in an environment to maximize its rewards through trial and error. In our work, we use a deep reinforcement learning algorithm known as proximal policy optimization. PPO is a policy gradient algorithm that optimizes a parameterized policy using gradients of the expected return with gradient ascent. It mitigates performance collapse seen in previous policy gradient algorithms by introducing a clipped surrogate function to control policy updates within a specified range. Thus, the overall function can be seen as the clipped surrogate objective, with the square error loss between the estimated value function and the target value, and an entropy per bonus term. This is an overview of our proposed methodology. We have a rule-based controller from which we collect historical data. We then train a policy using behavioral cloning to learn to mimic a policy that's closest to the expert agent. We then initialize these pre-trained weights for fine-tuning using reinforcement learning. To perform fine-tuning with PPO, as mentioned before, we initialize the actor with policy weights that were trained with the help of behavioral cloning. But if you notice one thing, is that the critic is initialized with random weights. Thus, We end up with a trained actor and an untrained critic. Inspired by the methodology described by Ramrakhya et al., we first train the critic during reinforcement learning. To do this, we divide the RL training into two phases. The first phase is called the critic learning phase. During this phase, we collect interactions from the environment using the trained actor to train the critic. In this phase, the actor can be completely frozen as described in Ramrakhya et al. However, from our experiments, we find that gradually increasing the actor learning rate gives the best results. During this time, the critic is initialized with a relatively high learning rate, which is decayed as training progresses. This brings us to our second phase, called the interactive learning phase. After the actor and critic learning rates are completely warmed up and decayed, they are stabilized for the remaining of the training process. We can keep the learning rates during this phase at the same or different learning rates. However, through our experiments, we find that keeping the actor and critic learning rates stable at different values yields the best results. We perform our experiments using simulations on the 5-zone environment provided by the Python library known as Sinergym. The environment is a single-story building divided into one indoor and four outdoor zones. Each simulated episode spans over the duration of 1 year. Within each episode, 35,040 intervals exist, lasting 15 minutes each. We simulate these experiments using three different weather conditions in our experiments. We run our experiments in hot, mixed, and cool weather. All our environments are initialized with stochasticity, meaning different episodes have slightly different weather as training progresses. The goal of Deep RL Agent is to reduce energy usage while maintaining a comfortable temperature range. This is achieved using an objective function that combines the weighted sum of energy consumption and thermal discomfort, which is normalized. Here, PT is the power consumption and TT is the current indoor temperature. Omega represents the weight assigned to power consumption, and thus 1 minus omega is the weight assigned to comfort. Lambda p and lambda t are scaling constants for power consumption and comfort penalties respectively. T upper and T lower are the upper and lower limits of the comfort temperature range. Discomfort is determined by calculating the absolute difference between the temperature and the comfort range. So if the temperature falls within the comfort range, the discomfort value is 0. This brings us to our evaluation results. For evaluation, we test the agent in the same environment but with a different seed and monitor its performance for a total of 5 years, that is 5 episodes, and average them. The averages are shown in the table you see in front of you. In our experiments, we compare the proposed methodology with different agents. First, we have the rule-based controller or the controller agent. Then we have the imitation agent, which is the behavioral cloning agent without fine-tuning. We include this agent to highlight the performance of the pre-trained agent before we fine-tune it with RL. Then we have the scratch agent, which is an RL agent trained without any pre-training. The default agent is a pre-trained agent that's fine-tuned naively. For this agent, we follow the same RL training methodology as Scratch agent. However, the weights of the actor are initialized with behavioral cloning. Thus, fine-tuning is naive, where a pre-trained actor and an untrained critic interact with each other. Finally, we include the agent described in Day et al., called previous, and follow the methodology described by them. We include these agents to show how fine-tuning can affect the performance of an agent and thus the need for a different fine-tuning methodology. As we can see in all three environments, the proposed agent gives the best rewards. Additionally, a proposed agent consistently and significantly outperforms the scratch agent. This implies that pre-training the agent helps it generalize better. But from the table, we can see that the fine tuning methodology plays an important role. So naively fine-tuning the agent can lead to poor policies being learned, as it is evident that the default agent cannot outperform the scratch agent. Along with this, a proposed agent also outperforms the previous agent. The policies learned by the proposed agent can maintain the indoor temperatures within the user's comfort bounds better than all other agents. While this might come at the expense of more power, the least power consuming agents are rule-based controller and imitation. But these two agents are the worst at respecting the user's comfort zone. Thus, the proposed agent is efficient at striking a balance between power consumption and user comfort. Thus, to summarize, naively training the trained actor and untrained critic together can lead to worse policies being learned than training from scratch. The proposed methodology outperforms rule-based controller, naively fine-tuned agents, agents trained from scratch, and prior work across all three weather environments. In our experiments, we noticed that warming up the actor too early could lead to overfitting, while warming it up too late could lead to underfitting. Thus, hyperparameter tuning is necessary. Choosing the correct actor and critic learning rate along with its annealing will have an impact on performance. Acknowledgements. This work was conducted with the financial support of Science Foundation Ireland Centre for Research Training in Artificial Intelligence. Thank you.